In this video, we will talk about what a partial derivative is. Okay, so I want to begin by looking at single variable functions and just doing a brief review of derivatives from single variable functions. So for example, e.g., let's say I had the function f of x equals x squared. Okay, so if I graph this function, and I have my x-axis and my y-axis, the graph of this is a parabola that's facing upwards and its vertex is at the origin. And I could take the derivative of this. So the derivative of this function is 2x. So just using the power rule. Okay, so the derivative here, f prime of x, equals 2x. So that's sort of the algebraic meaning, or the algebraic representation of the derivative here. Okay, but the derivative has a graphical meaning as well. So for example, if I were to look at the point on the graph where x is 1, it turns out the y value at that point is also 1. And I could draw the tangent line at that point. So the tangent line might look something like this. Okay, so that's the tangent line at the point 1, 1 has slope f prime of, and I'm going to plug in the x value, which is 1, f prime of 1, which is 2. So the slope of this tangent line is 2. Okay, so graphically, the derivative is the slope of the tangent line. Slope of the tangent line at the point x, comma f of x. And that is the graphical meaning of the derivative. It's the slope of the tangent line. But I can also think of the derivative as representing what's called, let's put this in black actually, as representing what's called the instantaneous rate of change, the instantaneous rate of change of our function at whatever x value we're talking about. Okay, so sometimes to abbreviate this, we call instantaneous rate of change, at least I like to call it IROC, for the instantaneous rate of change. All right, so I think of this as sort of a conceptual meaning for the derivative. It's an instantaneous rate of change. This value 2 sort of represents how quickly the function's value, so the function's outputs, are changing as we let x, or the input, change a little bit. All right, so that was a brief review of single variable functions. What about for a multivariable function now? So with a multivariable function, so I'm going to draw a graph. So let's say I have a z-axis and an x-axis and a y-axis. Okay, so 3D picture here, and I'll draw the negative directions. So I'm going to draw the graph of some multivariable function, f of x comma y equals z. Okay, but I'm going to draw kind of like a general picture here. So, okay, so let's say that directly above a point here somewhere on the xy plane, I get the surface. I have a surface, and the surface kind of curves this way, and then it starts to go up, and then I have a point here, and then it starts to go, I'm going to start having it go this way. So if I just draw where these are, if I project them down onto the xy plane, I might have a point here. If I do the same thing for this point, maybe this one projects down to a point over there, and then drawing some more of this. So drawing some more of this, maybe, I don't know, actually let me change that a little bit. Maybe I have it go this way, and then there's a point, and then I have it go this way. And of course, maybe my surface extends infinitely in all directions. But let's just imagine that it's something like this. So something like this, I have this graph of my function here. Okay, so now let's say that I were to look at a point on this surface. So if I were to look at a point on the surface, I'm going to just draw here. And when I look at that and project it straight down onto the xy plane, this might correspond to some x coordinate x naught and some y coordinate y naught. So we'd be plugging in those two values in for the x and in for the y in our function here to get whatever this z coordinate is. So what I want to do now is I want to try to draw a tangent line to this function at this point. But the key difference with the multivariable function is there are many different tangent lines that we could draw. So there are many tangent lines we could draw at our point x naught comma y naught, and then the z coordinate would be f of x naught comma y naught. There are many tangent lines that we could draw depending on the direction that we go. Okay, so let me go back up to the picture and draw in some of these directions. So for example, if I were to look, at this point where x naught y naught is, and just go purely in the y direction. Purely in the y direction, so I'm going to not move at all in the x direction. If I were to go purely in the y direction, I'd have a line sort of going like this. And now if I take that line and I sort of project it up onto the surface of my function, so maybe if I project this point up, maybe it's somewhere here, and then I start to draw my curve after I project this line up, and maybe it's starting to rise, and it rises, and then it does something like this. Okay. All right, so I have these arrows to sort of represent that. I was sort of considering going in this positive y direction here. So now if I draw my tangent line sort of along this curve here at that point, so at this point, ooh, that one a little bit too dark. Okay. So at that point, the tangent line would look something like this. So something like this would be my tangent line. So I would say that is a tangent line in the y direction, purely in the y direction, that orange one. But I could also have gone in the x direction. So if I hold y constant and I just go in the x direction, so that would be something maybe like something like this if I just draw it in the xy plane first. So I'll draw some arrows to indicate I'm going in the positive x direction. So if I take that line and I project it up onto the surface of my function, maybe it'll look something like, so maybe this point gets projected to a point like here. Whoops, okay. Maybe that gets projected to a point like right there. And then here, maybe it sort of, approaches this way, and then it's kind of like going down. It's kind of descending. Okay, it's kind of descending. Okay, so if I draw this tangent line, so this tangent line, this one would be more like, angling like this. That one seems like it's sort of sloping downwards. It seems like as x gets bigger, the z values are getting smaller. Okay, so that green one is the tangent line in the x direction. Okay, so this tangent line is parallel to the xz plane because we're holding y constant. And the other tangent line, this orange one, is parallel to the yz plane. Okay, so my drawing here is not perfect by any means. It's hard to draw these 3D drawings. But we really want to try to visualize this as that orange line being parallel to the yz plane, and this green line being parallel to the xz plane. Okay, so these two directions, the y direction and the x direction, they are maybe the two most common directions that we take derivatives in for multivariable functions. So let me just start a list of most common directions. Okay, so the most common ones are, we could take this tangent line and form it in the positive x direction. And that was one of the ones that we did up in that graph above. So when we do that, we write the slope as, and I'm going to introduce some notation, this curvy sort of d, f, a curvy sort of d, x. So the way I say this is I say del f, del x. So this curvy sort of d shape we pronounce that as del. All right, and this is called, this is notation for the partial derivative of the function f with respect to x. So that's what this df dx is. It's the partial derivative of f with respect to x. So that's what we'll call the slope when we look at it in this positive x direction. In the next video, we'll talk about, well, how do we actually compute this partial derivative? But in this video, I'm mostly focusing on, well, what does it mean graphically? What does it mean conceptually? So we can also think of this partial derivative as being an instantaneous rate of change. I'll call it IROC. IROC, instantaneous rate of change of my function f at the point x naught, comma y naught, comma f of x naught, y naught, if we go in the positive x direction, and I'll write that with x with a little plus sign, the positive x direction, and hold y constant. So that's another way that we can think about this partial derivative and what it represents, or think about this slope and what it represents. It's an instantaneous rate of change. All right, so we can also go in the positive y direction. In the positive y direction, and we saw that in the graph above. And when we do, the slope, we will notate that as del f del y. So that is, we call this the partial derivative of f with respect to y. Or if we think about that as an instantaneous rate of change, I won't write it down this time, but if we were to think about it as an instantaneous rate of change, we would be going in the positive y direction and holding x constant. Okay, so those are the two most common directions that we go in, and we form the slopes of these tangent lines. But sometimes we like to go in other directions. So not necessarily just in the positive x direction or the positive y direction. Sometimes we want to go in other directions. And these are called directional derivatives. And we won't talk about directional derivatives at all in our class. They're beyond the scope of our class. You would see these in a more complete multivariable calculus class. So in terms of our goals for this section, we've introduced what a partial derivative is and describe what it sort of represents graphically in terms of the slope of a tangent line, and conceptually in terms of instantaneous rate of change. In the next video, we'll actually start to do examples where we compute partial derivatives algebraically.